start today off with a motivating example. We're going to go and compute two different vector line integrals over three different curves, and use this to motivate a lot of important ideas. So we want to go and compute the line integrals of the vector field negative yx and the vector field x plus 1 comma y over the following three curves who go from the point minus 1, 0 to 1, 0. First, we'll integrate them over the straight line curve in blue. Then we'll integrate them over the parabolic arc y equals 1 minus x squared in red, and then we'll integrate them over the circular segment x squared plus y squared equals 1. Now, to compute any one of these line integrals, say the first one, negative yx dot ds, which is equivalent to the vector field of negative y dx plus x dy over these line integrals, we're going to have to come up with parameterizations for each one of them. And these parameterizations have been chosen because they represent three most common types of curves we parameterize. The blue curve represents a straight line from one point to another point. We already have seen how to parameterize straight lines as x equals x naught plus at and y equals y naught plus bt, where x naught y naught is the initial point on the line, and the vector ab is a vector who points towards the terminal point. So in our case, we could use the initial point minus 1, 0, and then use as the vector who points from minus 1, 0 to 1, 0, which is the vector 2, 0. And so we would have a vector valued function c of t equals negative 1 plus 2t comma 0. The time interval over which this would be valid, well, let's see, when t is equal to 0, we'll hit the first point, and when t is equal to 1, we hit the second point. So we're flowing in the correct direction. The red curve represents the graph of a function, something who takes the form y equals f of x. If you ever want to parameterize the graph of a function from left to right, the easiest parameterization is to set x to be the t value, and then to set y equal f of t. This will give us a function who, when we eliminate the parameter, is exactly the graph we're looking for. So in our case, we'll set x to be t, and then we'll set y to be the function 1 minus t squared. So we can turn this into a vector-valued function c of t is equal to t comma 1 minus t squared. The time interval over which this is valid, well, let's see, we'll hit the left endpoint when time is equal to minus 1. We'll hit the right endpoint when time is equal to 1. And so we're flowing in the correct direction. Finally, the green curve represents a circle or an ellipse. If we have any kind of circle or ellipse that has an axis of a units long in the x direction and b units long in the y direction, then the parameterization x equals a cosine of t and y equals b sine of t will parameterize the circle in the counterclockwise or positive direction. So in our case, we could take x equals cosine of t and y equals sine of t, since we're looking at a circle of radius 1, and so both of these measures should be 1. So our vector-valued function would be cosine of t sine of t. And the time interval over which this is valid, well, we know that tracing out a circle, time equals 0 is the starting point. So this would be time equals pi at this point, and then time equals 3 pi over 2, and then time equals 2 pi when we cycle back. So we'll do this from time equals pi to 2 pi. And so we've parameterized each of the three separate segments. This will allow us to go and compute each of the three different line integrals. So let's work out this line integral here under the straight line parameterization. So we would integrate it from 0 to 1 of negative y, well, the y value is 0, times the derivative of the x value, which is 2, plus the x value, which is negative 1 plus 2t, times the derivative of the y value, which is 0, dt. So that will simply be the integral from 0 to 1 of 0 dt, which will evaluate to 0. Over the parabolic segment, we're going to integrate from minus 1 to 1 the negative of the y value, so negative 1 minus t squared, times the derivative of the x value, which is 1, plus the x value, t, times the derivative of the y value, negative 2t, dt. So if we clean this up, this is the integral from minus 1 to 1 of minus 1 plus t squared minus 2t squared dt, or the integral from minus 1 to 1 of negative 1 plus t squared dt. If we integrate this with respect to t, we're going to get negative t plus 1/3 t cubed evaluated from minus 1 to 1, or negative 4/3. And finally, if we look at the green parameterization, that's the integral from minus pi to pi, 2 pi, sorry, of the negative of the y value, negative sine of t, times the derivative of x, which is negative sine of t, plus the y value, plus the x value, cosine of t, times the derivative of the y value, cosine of t, dt. So we're integrating sine squared plus cosine squared, which means we're integrating 1 dt, or pi. So in each one of these cases, we have one vector field. We're integrating it over 3 different paths who go from minus 1, 0 to 1, 0, and in each case we get 3 different values. Now, getting different values really shouldn't be all that mysterious right here. Remember that a line integral measures how much of a vector field is running tangentially to the flow of the curve. Now, you might remember we actually plotted the vector field minus yx in the previous lecture, and the result should be kind of consistent with this. The vector field was orthogonal to the x-axis. It was pointing straight out of it. And since that the vector field was at right angles to the curve, to the horizontal curve, it makes sense that the line integral should be 0. On the other hand, the red curve is moving against the flow of the vector field. Or, said differently, the vector field is flowing opposite the flow of the curve, and that would explain the negative value right here. On the other hand, the green curve is flowing in the same direction as the vector field, which would explain the positive value right here. Even though all of these curves have the same starting and stopping point, there's absolutely no reason to believe that they should ever have the same integral value, because the vector field could do all sorts of crazy stuff in between. Keep that in mind as we take a look at the next example. Let's focus on this particular integral, the line integral over a curve of x plus 1 comma y ds, dot ds, which we can express as the integral of x plus 1 dx plus y dy. So over the blue straight line, this would become the integral from 0 to 1 of x plus 1 dotted with the derivative of x, which is 2, plus y, which is 0, times the derivative of y, which is also 0, dt. So this will become the integral from 0 to 1 of 4t dt. That means we're looking at t squared, 2t squared, evaluated from 0 to 1, which would be 2 minus 0, or 2. Next, we'll take a look at the red integral, or the red curve, sorry. That was parameterized from minus 1 to 1, x t plus 1 times the derivative of x, which is 1, plus y, which is 1 minus t squared, times the derivative of y, which is minus 2t dt. So if we clean this up, this is the integral from minus 1 to 1 of t plus 1 minus 2t plus 2t cubed dt. Or the integral from minus 1 to 1 of 1 minus t plus 2t cubed dt. That integrates to t minus 1 half t squared plus 1 half t to the 4th power, evaluated from minus 1 to 1, which is 2. Finally, if we integrate along the green curve from pi to 2 pi, we're going to have x plus 1, so the cosine of t plus 1, times the derivative of x, which will be negative sine of t, plus y, which is the sine of t, times the derivative of y, which is cosine of t, dt. So this will become the integral from pi to 2 pi of negative sine of t cosine of t minus the sine of t plus the sine of t cosine of t dt. Well, notice that these two terms cancel. And so we're really just left with the integral of negative sine of t dt. But that's exactly cosine of t evaluated from pi to 2 pi. And so we get 2. So in this case, we used one line integral, and we had 3 different curves who went from minus 1, 0 to 1, 0. But in each time, we got 2 as a value right here. Is that just a lucky fluke, or is it possible that this particular vector field always gives us the same line integral no matter what path we pick? That's going to be our starting topic. A vector field f is called path independent if the line integral of f dot ds over c is equal to the line integral of f dot ds over d for any paths c and d with the same initial and terminal points. In other words, if you had a starting point P and an ending point Q, and you picked any path whatsoever C, and then some other path who has the same starting point and the same ending point D, then you should always get the same line integral over the one path C as you did for the other path D. Now, it might seem pretty amazing that any kind of vector field could have this property, that it could be built in such a way that no matter how you draw the curve, you always get the same value, no matter what. But it turns out that there's one type of vector field for which this works all of the time. And those are the gradients. Gradient fields are always path independent. This is a consequence of something called the vector field fundamental theorem of calculus. Specifically, that says this. The fundamental theorem for vector fields states that if big F is the gradient of some function little f, then the line integral of big F dot ds over some curve is equal to little f evaluated from the initial point of C to the terminal point of C. Notice that the formula on the right-hand side only depends on where C starts and where C stops, but not the path that C takes in the middle. And so this shows us that if a vector field is the gradient of a function, it must be path independent. It turns out that the proof of this statement is actually pretty straightforward, and it's based off of tools we've already got. So let's assume that we have such a function, and let's work out what its line integral would be. So this would be the line integral of the gradient of f dotted with ds over the line, or over the curve C. Now, if we had a parameterization, this would be the integral from a to b of the gradient of f evaluated on the curve C of t, dotted with c prime of t dt, because that's one of our formulas for computing a line integral. But this expression right here, the gradient of f of c of t dotted with the derivative of c of t, that's exactly the derivative with respect to t of the function f of c of t. And so we're integrating from a to b this expression right here. Well, notice that the expression in purple is a function of one variable, so we can apply the original fundamental theorem of calculus. So we need only cook up an antiderivative of the derivative of f of c of t. Well, that would just be f of c of t, which we can evaluate from a to b. So that gets us f of c of b minus f of c of a. But what's c of b? C of b is just the terminal point of the curve. And c of a is just the initial point of the curve. And that's exactly what we wanted to say up here. So in the context of the problem we had just done, it looked as though the vector field x plus 1 comma y was path independent. We could prove this assertion if we could show that it was the gradient of some function. So is it the case that x plus y comma y is equal to the gradient of some function f? That is, does it take the form f of x and f of y? Well, you might remember we had a test that would suggest whether or not it's a candidate for it. And that test involved taking the partial derivative of the first component with respect to y and setting it equal to the partial derivative of the second component with respect to x. In this particular example, the derivative of the first component with respect to y is 0, the derivative of the second component with respect to x is 0. So it certainly is a possible candidate for a gradient. So let's see if we can dig up a function who would work. We would need the derivative of f with respect to x to be x plus 1, and the derivative of f with respect to y to be y. So let's see if we can figure out what f would have to be. On the one hand, if we integrate the expression x plus 1 with respect to x, we're going to get 1 half x squared plus x, plus anything involving the variable y, who would have disappeared in the partial derivative. On the other hand, if we integrate y with respect to y, we're going to get 1 half y squared, plus anything that involves x. So is it possible to put these two statements together into one function? Well, a reasonable function might be f of xy equals, it has to have a 1/2 x squared, it has to have an x, and it has to have a 1/2 y squared to make these three components happy. And we could actually double check that the gradient of this function is in fact x plus 1 y. And so this one works. We now know that this function must be path independent. In fact, if we use this vector-valued fundamental theorem, it tells us that the integral of the vector field x plus 1 y dot ds, it must equal our function 1/2 x squared plus x plus 1/2 y squared, evaluated at the initial point of all of our curves. Well, all of our curves start at the point -1, 0, to the terminal point 1, 0. Now, if we plug in the terminal point of 1, 0 into here, we're going to get 1/2 plus 1 plus 0. If we plug in the initial point, we're going to get 1/2 minus 1, 0. And so that will get us 1/2 plus 1 minus 1/2 minus minus 1, or 2, which is what we found last time. Compute the line integral of 2xy e to the y dx plus x squared 1 plus y e to the y dy, where c is the plane curve indicated below. Now, the first thing I would do when I'd see this is I'd notice that there's no way in heck that we're ever going to be able to parameterize this. And so our only hope is that the vector field that we're integrating, specifically the vector field 2xy e to the y, comma x squared 1 plus y e to the y, is the gradient of some unknown function, because then we could use the fundamental theorem and simply use the initial and terminal points. Is it possible that f is the gradient of some unknown function? Well, we can do the check real fast. Let's take the derivative of del f1 del x, or del f1 del y, and del f2 del x, and see whether or not these things match. The derivative of the first component of f with respect to y is just going to be, well, the 2x will come along for the ride. The y e to the y will require the product rule, so the derivative of the first times the second, plus the first times the derivative of the second. And so if we pull out an e to the y, that's 2x e to the y times 1 plus y. Now if we focus on the second coordinate, the 1 plus y e to the y is a constant, so it comes along for the ride. The derivative of x squared is 2x. So that gets us 2x e to the y, 1 plus y. Since these two expressions match, this at least has a chance of being the gradient of some function. So now let's see if we can figure out what it would have to be. So if this were equal to the gradient of some function f, then it would have to be that the first component of the vector field would be the derivative with respect to x, and the second component of the vector field would be the derivative with respect to y. And so that would mean that this unknown function would have to satisfy two sets of equations at the same time. If we integrate 2xy e to the y with respect to x, or if we integrate x squared times 1 plus y e to the y with respect to y, that f would have to satisfy both of these two conditions simultaneously. Well, the first condition just says, let's see, the y e to the y is a constant, the antiderivative of 2x would be x squared, so x squared y e to the y, plus things that are constant from x's point of view, so stuff with y. So f would have to take the form x squared y e to the y plus some stuff. What about the second integral? Well, notice that the x squared comes along for the ride, so this is really just x squared times the antiderivative of 1 plus y times e to the y, dy. Well, a problem like this is an excellent candidate for integration by parts. So let's do the integration by parts work over here. I would take as my derivative terms the 1 plus y, since that's algebraic, and we'll simply integrate e to the y over and over again. If we differentiate once, we get 1. If we integrate once, we get e to the y. We differentiate twice, we get 0. We integrate twice, we get e to the y. And since we've got a 0, we're ready to build our table. Plus, minus, plus, integral. And so we know that the antiderivative has to look like positive 1 plus y times e to the y minus 1 times e to the y plus the integral of 0 dx, or dy, which in this case would contribute nothing. So if we expand this piece out, we're going to get e to the y plus y e to the y minus e to the y, or y e to the y. And so we found an antiderivative for 1 plus y e to the y dy. Substituting this in, we find that f has to look like x squared times y e to the y as an antiderivative of y plus anything that's a constant from y's point of view, which is stuff in x. Is it possible to find an f who satisfies these two equations at the same time? Well, actually, yeah, this one's kind of pretty easy. Why don't we just set f to be this expression right here? So let's set our function f of xy to be the equation x squared y e to the y. And we could check very quickly that, in fact, the gradient of f is the original vector field f. So now that we've found this function f, we can go and work out the line integral. The line integral over the curve c of our vector field dotted with ds is simply going to be the function we found, little f, evaluated from the starting point 1, 0 to the stopping point 2, 1. So that will be x squared y e to the y evaluated from 1, 0 to 2, 1. So at the point 2, 1, we're going to have 2 squared times 1 times e to the 1. At the initial point, we're going to have 1 squared times 0 times e to the 0. That piece cancels, and so we're left with a grand total of 4e. And so there's the contour integral. And we didn't even need to parameterize it this time around. Let's change gears here for just a second and talk about some physics applications before we get too much farther. It turns out that vector fields play a crucial role in physics. For example, if you had some kind of a mass, Newtonian physics says that every mass imparts a gravitational pull on any other particle around it. Now, how do we model this gravitational pull? Well, at any single point, this object feels a gravitational pull towards the mass in question, and the force of this pull increases as we get closer to the object and weakens as we get farther back. In fact, if we were to plot the gravitational pull at every single point, we would come up with a vector field. In fact, this gravitational field is known to be given by g of the vector x is equal to the current position of x, pointed in the opposite direction, and then divided by the length of that cubed. As a second example, suppose that you had two electrical charges. You had a charge which was positive and a charge which was negative. So if you happen to have another positive charge floating around out in space, it would feel two different forces acting on it. It would be pushed away by the like positive charge, but it would also be pulled towards the negative charge. If the particle was very, very close to the original positive particle, then the pushing away would be very strong and the pull would be very, very slight. Whereas if the particle was very, very close to the negative charge, the pull would be very strong, but the push would be kind of minimal. And so if we were to sort of draw the net vector at every single point of these forces, we would once again see a vector field. As a third example, suppose you had a bar magnet. Now, a magnet always has a north and a south pole, and that causes every other piece of magnetized metal to sort of align itself up with it. If we were to take any other magnet, well, that magnet is going to feel a magnetic pull right here, where its south pole will want to be pulled towards the north pole, and its north pole will want to be pulled towards the south pole. And again, the farther the magnet is away, the stronger or weaker those pulls will be. And if we were to go through and mark down the magnetic field pull at every single point, we'd get something like this. So the upshot is that vector fields or force fields play a big role in physics. Gravitational fields, electric fields, and magnetic fields are the heart and soul of classical Newtonian and Maxwellian physics. With that in mind, I can give an actual physical application to what a particular line integral might measure. Imagine that we had some kind of a curve. And the idea is we're going to imagine a particle who's on this curve, and this particle is going to sort of move its way along this track from a beginning point to an ending point. Well, as the particle moves, the force field is pushing and pulling on it at different points. Sometimes it's pushing in some directions, sometimes it's pushing in other directions right here. And we can ask, what's the work done by the force field in moving the particle along the curve C? If a particle is moved in a straight line direction, D, and a constant force is applied on it the entire way through, F, then basic physics says that the work done is equal to the force dotted with the displacement. But in this case, we have a varying force field and a curve who's not straight. But we could imagine chopping this curve up into lots and lots and lots of little tiny pieces. Over a single tiny segment, we could imagine that the force is more or less constant throughout that entire piece. And so the work done on this piece right here would be approximately that force dotted with this displacement. Now, this displacement vector, again, if the segment is small enough, could be well approximated by the direction of the unit tangent. But the unit tangent is actually, in a tiny, tiny chop, is very, very long right here. So we need to scale the unit tangent down by how long this piece of segment is, which is what we were calling delta S a while ago. So the vector t times delta S approximates the displacement over this tiny piece. Hence, the total work done over this curve is going to be summing up all of these little tiny, well, tiny segments of work. So we will be summing up little tiny bits of force times the unit tangent vector, delta S. Well, this is an approximation. If we want to make that approximation exact, we would take a limit. And so we would take the limit of the sums of f dot t delta S. But that's exactly what the integral of f dot t ds is supposed to represent. And the other symbol for that is f dotted with ds evaluated over c. And so what we've just shown is that a vector line integral measures the work done by that vector field on moving the particle over the curve c. As a result, in physics, a line integral is sometimes known as a work integral. Now, if we look back at the three sort of essential vector fields that we were talking about in physics, the gravitational vector field, the electric charge vector field, or the magnetic vector field, there is a particular property that ends up being crucial in physics, and that property is that the amount of work it takes to move a particle along any path back to its starting point, no matter where you start and no matter what path you take, the amount of work it takes to move a particle back to its starting point in any one of these fields is zero. A physicist would say that gravity or electric charge or bar magnets conserve work. In mathematics, we say that a vector field f is called conservative if the line integral over any closed curve is always zero. It turns out that the real universe around us is chock full of conservative vector fields. But how would we find them mathematically? Well, it turns out that a vector field is conservative if and only if it's path independent, that this physics concept and the math concept that we looked at the beginning are in fact the same thing. The basic argument might go something like this. Suppose you had a vector field who you knew was path independent, and you wanted to go and show that that vector field was conservative. So what we could do is we could go and take some random closed curve and integrate over it. Now let's take that curve and let's chop it up into 2 points. Say a point here at the point P and some other point at the point Q. It doesn't really matter where these points are. And what I'm going to do is I'm going to take the curve C and chop it up into 2 pieces. It'll have this right-hand piece, who I'll call A, and it will have this left-hand piece, who I'll call B. To prove that it's conservative, I'd like to go and show that the line integral over C, which is a closed line integral, is equal to 0. But by our properties of line integrals, the line integral over C is just going to be the line integral over A plus the line integral over B, because I chopped C up into 2 smaller pieces. Imagine for a second we took B but made B flow in the opposite direction. So that would be negative B. One of our rules of line integrals is that if we negate the direction of a path, then we negate the value of the vector field. So we would have that this is equal to the line integral over A minus the line integral over negative B. But now, ignore C for just a second. A and negative b are two different curves who have the same starting point, Q, and the same ending point, P. Since the vector field is assumed to be path independent, these two values right here have to be the same. And so they do in fact cancel, and so we have checked that the integral over a closed curve is 0. The same basic idea can be used to show that if the line integral over every closed curve is 0, then the vector field is path independent. So it turns out that these two concepts are in fact exactly the same thing. That is, that integrals over closed loops always evaluate to 0, and that the line integral over a curve depends only on the endpoints of C. We also saw that a vector field was guaranteed to be path independent if it could be expressed as the gradient of some other vector field. This is well known to physicists, and in fact physicists have gone out of their way to give this kind of a function a special name. This is sometimes known as the potential function for the vector field f. It turns out that this last condition is also equivalent to being path independent. A vector field is path independent if and only if it's a gradient field, if and only if it has a potential function. Now, the equivalence of being path independent and being a gradient field is actually an important result in Calculus 3, and it merits a little bit of a proof, but I'm going to delay that until our next podcast. All I would like to say is that these three conditions together are called the equivalent conditions for a conservative vector field, and a lot of times in Calc 3 books, we simply use the phrase conservative to mean any one of these three properties, since they're interchangeable. Show that the vector field f equals 3x squared yz plus zy e to the x, comma, x cubed z plus e to the xz, comma, x cubed y plus xy e to the xz is a conservative vector field. Now, based on what we had just talked about, being a conservative vector field is the exact same thing as saying that f is a gradient field, that the vector field f has a potential function, little f. What would such a function look like? Well, its derivative with respect to x would have to match the first component of the vector field f. Its derivative with respect to y would have to match the second component, and its derivative with respect to z would have to match the third component. So such a function f would have to satisfy three separate integration properties. If we were to integrate 3x squared yz plus zy e to the xz with respect to x, or if we were to integrate x cubed z plus e to the xz with respect to y, or if we were to integrate x cubed y plus xy e to the xz with respect to z, these should all describe the same function. Well, let's see what they do describe. If we integrate the first part, the integral of 3x squared yz, 3yz is a constant, comes along for the ride. The integral of x squared is x cubed over 3, so we get x cubed yz. On the other hand, the integral of zy e to the xz with respect to x, zy comes along for the ride. The derivative of e to the xz will be e to the xz divided by z. So the z's cancel, and we get y e to the xz. And that's true plus anything that involves just y and z, parts who would have been differentiated out with respect to x. Focusing on the second integral, if we integrate x cubed z with respect to y, we get x cubed yz. If we integrate e to the xz with respect to y, again, that's a constant, so we're going to get e to the xz times y, plus, well, stuff that involves only x's and z's. And finally, if we integrate the last part with respect to z, the integral of x cubed y with respect to z, x cubed y is a constant, so we'll just tack on a z. On the other hand, xy is a constant, it comes along for the ride. The integral of e to the xz will be e to the xz divided by the constant x. So the x's will cancel, and we'll get y e to the xz, and then anything involving just y's and x's. So could we find a function f who makes these three statements happy? Just notice that all three of our statements agree on this part right here. So if we took f of x, y, z to be the function x cubed yz plus y e to the xz, we could quickly double check that its gradient does in fact do the job right here. The gradient of f is capital F. So since capital F has an antiderivative, we now know that capital F must be conservative. Now this last example, even though it was fairly straightforward, shows just how much work goes into finding a potential function. It takes a lot of effort to show that something is conservative. In fact, each of our three equivalent conditions for a conservative vector field involves something fairly complicated. We either have to check every possible closed curve to evaluate to zero, or every possible curve whatsoever, or we have to dig up a specific function which involves several integrals and then trying to find common patterns. Is there a more efficient way to test that any one of these three crucial properties holds? You might remember that we had a test that could be used to detect candidates for gradient fields. Specifically, the gradient test, which said that the vector field f had to satisfy three different equations among its component functions. That was if you were in R3. If you were in R2, then you only had to satisfy that first equation. We know from last time that if you are a gradient field, then you have to satisfy these equations, because they simply boil down to the equality of mixed partials. But I made a big deal last time about saying that it wasn't true that just because you satisfied these three equations that you had to be a gradient, that this statement was in fact false. I didn't give you any reason to believe it last time, so let me rectify that this time. As a counterexample, consider the vector field f equals negative y over x squared plus y squared, comma x over x squared plus y squared. If we tried applying the gradient test, well, let's look at our two different partial derivatives. We take the partial derivative of f1 with respect to y, and the partial derivative of f2 with respect to x. Now, if we differentiate the first expression, that's the partial derivative with respect to y of negative y times x squared plus y squared to the minus 1. So using the product rule, we'd have the derivative of the first times the second, x squared plus y squared to the minus 1, plus the first piece, minus y, times the derivative of the second, which would be minus 1 times x squared plus y squared to the minus 2 times the derivative of the inside, which is 2y. So if we clean this up, we're going to get negative x squared plus y squared plus 2y squared times x squared plus y squared to the minus 2. Oh, this is to the minus 1. Now, if I pull out the common power of x squared plus y squared to the minus 2 from both pieces, we're going to have x squared plus y squared to the minus 2. Factors out of the first piece will leave me with a negative x squared plus y squared to the minus first power, and from the second piece, a 2y squared. And so if we clean that up, this will go in the denominator, so we'll have x squared plus y squared squared in the denominator, and in the numerator we have negative x squared minus y squared plus 2y squared, or y squared minus x squared. Now let's focus on the second partial derivative, which I'm going to have to move down a step. The partial derivative of f2 with respect to x. We get an x squared plus y squared squared in the denominator, and in the numerator we have y squared minus x squared. And so these two things match. Del f1 del y is equal to del f2 del x. The gradient test checks out. However, this function doesn't have a potential. This vector field doesn't have a potential function, and I can show that by showing that it's not conservative, which is one of the things that's equivalent to having a potential function. To show it's not conservative, I'm just going to compute the line integral of the vector field f ds over the unit circle centered at the origin of radius 1. I can parameterize the unit circle by cosine of t, y equals sine of t, with t going between 0 and 2 pi. If it was a conservative vector field, if it had a potential function, this would evaluate to 0. But let's see what it does evaluate to. So I want to integrate negative y over x squared plus y squared dx plus x over x squared plus y squared dy, evaluated from 0 to 2 pi. So if I plug in everything, we're going to have 0 to 2 pi, negative y, negative sine of x, or sine of t, over x squared plus y squared, well this is the unit circle, x squared plus y squared is 1, times the derivative of x, which is negative sine of t dt, plus x, which is cosine of t, over x squared plus y squared, cosine squared plus sine squared is 1, times the derivative of y, which would be cosine of t, dt. So if we clean this up, we have the integral from 0 to 2 pi of negative negative sine of t squared plus cosine of t squared dt. Well, this expression is just 1 again. So we're integrating from 0 to 2 pi, 1 dt. That gets me t evaluated from 0 to 2 pi, or 2 pi, which is not 0. So this example shows that it's possible to satisfy the gradient test, but to not be conservative. The previous example demonstrates that just because you satisfy the gradient test, you don't have to be a gradient field. However, it's possible to modify the test slightly in order to make it completely functional. You might notice that the counterexample that we had looked at was discontinuous at a particular point right here. And it's that discontinuity that caused the problem. So in other words, f didn't actually satisfy the gradient test at the point 0, 0. It turns out that that's the crucial problem. If we modified the gradient test by saying that it satisfied these equations for all values of x in R3, then in fact, the reverse implication would hold, and the gradient test would be enough to say that the vector field is the gradient field, or was conservative, or was path independent. In fact, we can weaken this condition a little bit more as follows. In mathematics, the phrase simply connected means that a set has no holes or punctures. So for example, all of R2, the plane, would be a simply connected set. Or say quadrant 1 would be a simply connected set. Or even the inside of a circle would be examples of simply connected sets. On the other hand, the outside of a circle in R2, or a blob with a blob taken out of it on the inside, like a giant figure 8, or say all of the plane with a single point punctured out of it would be examples of not simply connected domains. It turns out that being simply connected is strong enough to make the gradient test a predictor for gradients. Specifically, if the vector field f is a gradient field, then it will always satisfy the gradient test. Conversely, if the domain of f is simply connected, then the gradient test will imply that the vector field is conservative. So the gradient test is a perfect predictor of conservative vector fields as long as the domain remains simply connected. This last result is one of the deepest and most crucial results in all of Calc 3, and so I want to give you some argument for it, but it's going to have to wait until the next podcast. However, I would like to point out one interesting consequence of this with respect to our counterexample vector field. The original vector field was discontinuous at 0, 0 only, which meant that its original domain looked something like this guy right here, a non-simply connected subset. However, suppose we were to take this function and restrict it to the right half plane, so that we don't hit 0, 0, but we hit everything in quadrants 1 and 2. Well, then this set is simply connected, and so that would mean that the function f should be the gradient of somebody according to our result. This is a simply connected domain. And in fact, this is true. The function f of xy equals the arctangent of y over x would be such a potential function. Interestingly enough, if we were to actually go and take the upper half plane instead of the right half plane, this is another simply connected subset. And so that would mean that our original counterexample function should be the gradient of somebody. Except this time, we can't use the original arctangent function because this function right here would be discontinuous along the y-axis. Nevertheless, the result says there is a function out there who is its potential, and with a little bit of finagling, you can work out that it's the arc cosine of x over the square root of x squared plus y squared. So it turns out that this one vector field does not have a potential on its whole domain because its whole domain is not simply connected. But if you were to take this set and chop it up into any simply connected subset, such as this one or this one, then it will have a potential function, although that potential function might actually change depending on the set you've got. This is just an interesting consequence. So if we were to return to this example before, which took a lot of effort on our part, We can now re-examine it in light of this new result. Notice that the domain of f would be the domain of each one of its individual pieces. Well, since each one of its components is either a polynomial or a product of polynomials and exponentials, the domain of f is all of R3, which is simply connected. So that means it's going to satisfy being a conservative vector field if and only if it satisfies the gradient test. So we can simply work out the three partial derivatives of the gradient test, del f1 del y equals del f2 del x, and del f1 del z equals del f3 del x, and del f2 del z equals del f3 del y. And as long as these three conditions hold, we'll know it's conservative. And this just amounts to taking three partial derivatives. So let's work our way through each one of these things. If we take the partial derivative of the first component with respect to y, we're going to get 3x squared z plus z e to the x z. On the other hand, if we take the derivative of the second component with respect to x, well, let's see. We're going to get 3x squared z plus the derivative e to the xz will be e to the xz times the derivative inside, which is z. Those two equations, check. Now we can focus on the second one, the derivative of the first component with respect to z. Well, if we differentiate the first component with respect to z, we're going to get 3x squared y plus, we're going to have to use the product rule in the second part. So we have the product of yz times e to the xz. The derivative of the first is y times the second, plus the first piece, zy times the derivative of the second piece. The derivative of e to the xz with respect to z will get us out an extra x. Is that the same as the derivative of the third component with respect to x? Well, let's check it out. The derivative of the third component with respect to x, the first piece will get us a 3x squared y. The second part is going to involve a product rule again. So the derivative of the first is y times e to the xz, plus the first part, xy, times the derivative of the second. The derivative of e to the xz is e to the xz times the derivative of the inside, which is z. And so in both cases, we have 3x squared y plus y e to the xz plus xyz e to the xz. These two equations match. The second of the two parts of the component test, or of the gradient test, are taken care of. Finally, let's focus on these last two bits. The derivative of the second component with respect to z, well, that's going to be x cubed plus e to the xz times the derivative of the inside, which is x. On the other hand, the derivative of the third component with respect to y is going to be x cubed plus x e to the xz. These two equations check out. They are in fact equal. And so the three equations of the gradient test check out. Since the domain is simply connected, we can conclude that f is conservative. Notice that this was a much faster approach. Compute the closed line integral of 2xy sine of xy squared plus x squared y cubed cosine of xy squared dx plus 2x cubed y squared cosine xy squared plus x squared sine xy squared dy, where c is the contour shown below. Now, the first thing to notice about this contour is that I have one piece of data about it, and I have no way of parameterizing it. So we'd better hope that the vector field is conservative, because if it was, then this line integral would evaluate to 0 and we wouldn't have to parameterize anything. So we need to only check that this vector field right in here is a conservative vector field. In component form, we can write f like this, and we notice that its domain would be the whole of R2, which is simply connected. So the only way that this function can be conservative is if it satisfies the gradient test. So we really only have to check del f1 del y and del f2 del x, and see whether or not those two things match up. First, I'm going to throw out that contour because I'm hoping I don't need to use it. And let's focus on this first derivative, the partial derivative of the first component with respect to y. That would be the derivative of this expression here. So notice that the first term will require the product rule, so we'll take the derivative of the first, 2x times the second piece, sine of xy squared, plus the first piece, 2xy, times the derivative of the second piece, which will be the cosine of xy squared, times the derivative of xy squared with respect to y, which will be 2xy. Then we have a second term, so we'll have to use the product rule again. The derivative of the first will be 3x squared y squared times the cosine of xy squared, plus x squared y cubed times the derivative of that expression, which will be negative sine of xy squared, times the derivative of the inside, which is 2xy. So if we clean this up, we're going to have 2x times the sine of xy squared plus 4x squared y squared times the cosine of xy squared plus 3x squared y squared times the cosine of xy squared minus 2x cubed y to the fourth times the sine of xy squared. And notice that these two middle terms could be combined into a single 7x squared y squared cosine of xy squared term. Let's focus on the second piece now, the derivative of f2 with respect to x. So that would be this expression right here. So if we work our way through it using the product rule, the derivative of the first part will be 6x squared y squared times the cosine of xy squared plus 2x cubed y squared times negative sine of xy squared times the derivative of that expression with respect to x, which is y squared, plus the derivative first, 2x times the sine of xy squared, plus the first part x squared times the derivative of the second, which is cosine of xy squared, times the derivative of the inside, which is, with respect to x, y squared. That simplifies to 6x squared y squared times the cosine of xy squared minus 2x cubed y to the fourth times the sine of xy squared plus 2x times the sine of xy squared plus x squared y squared times the cosine of xy squared. Notice that these two terms here can be combined to form a single 7x squared y squared cosine xy squared. And so now we can ask the question whether or not these two things are the same. We'll notice that they both have a 2x sine xy squared, they both have 7x squared y squared cosine xy squared, and they both have a negative 2x cubed y to the fourth sine x y squared. So they are in fact the same thing. Since this checks out, we now know that f is conservative, and therefore, since it's conservative, this closed integral must evaluate to 0.